All right, so now we're going to talk about heating curves. And we did this in class. We made our own heating curve. We took a bunch of ice and were able to melt that ice. And we saw that there was a flat line, like right here, when we started, because all the energy from the hot plate was going into melting the ice. None of the ice was getting any hotter because if there was any energy to be gained, it was turning the solid to a liquid. And then when all the ice was gone, all the solid was gone, it was nothing but liquid. We were then able to heat it up like this part of the curve. And we saw the temperature rise until it got to the point where it was boiling. At that point, the temperature again would flatten out because all the energy was going from the liquid to the gas phase, and no energy was getting put into making the temperature go up. And so on this graph here, this represents a graph of any substance capable of being a solid, liquid, and a gas. It would look like this, where A down here, this part at the bottom, lower temperature, would be the solid area. And all the energy you put in at this point goes to kinetic energy. Your temperature increases. Your B area, that first flat part, will be solid transforming to liquid. That's the phase change. Temperature will be constant at that point. Then the C part is where you have liquid. So this could be liquid. We're using water here, but if this were, lead, this would be solid lead at A, lead melting into liquid at B, and then C would be liquid lead. So part C would have your liquid phase, and your kinetic energy would be increasing, your temperature would be increasing, and then when you become flat again, as you do here at part D, you're transforming from liquid to gas. So your phase change is what's happening. Your temperature remains constant. In this case, you're boiling liquid to gas. And then E would be the gas phase. So now you're just heating up the gas phase and kinetic energy goes up again. Um, the things you need to know besides all that, which phase exists at which part of this graph, is that you can glean from this your boiling point for the substance, which would be wherever this flat part is. The temperature associated with that flat part is therefore the boiling point of the substance you're talking about. That would be the higher of the two flat areas, and that your lower flat area corresponds to the melting point or freezing point, depending which way you're going, of that substance. So here with ice, 0 degrees is the freezing point, also the melting point of ice. So that flat area corresponds to 0 degrees, and the boiling point of water is 100 degrees. So that's why this flat area corresponds to the 100. All right. So we use these delta H terms to talk about energy changes in reactions. And so when water solid goes to water liquid, there is a change in energy, and the energy is called the heat of fusion. And that is 334 joules per gram of water. So for every gram of ice you want to convert to liquid water, you need 334 joules of energy. That's an endothermic reaction. And likewise, if we want to go the other way, liquid to solid, that would be an exothermic reaction where we take out 334 joules to turn liquid water into solid ice. And that takes energy out because your freezer is taking heat away, right? That's what a freezer does. So, in questions of this nature, we would use this equation that Q equals the mass times the heat of fusion. If we asked you about how much heat is needed to heat up ice to melt it to liquid, or if any other solid we were trying to melt, we would have to give you the delta H fusion of that solid, and you would multiply it by the grams of that solid you're trying to melt. Similarly, when liquid becomes gas, that's another phase change that we call the delta H vaporization. And as you can see here, the vaporization energy is significantly more than the fusion energy. That makes sense if you consider what it is you're doing to turn something from liquid to gas. You're turning a bunch of clumped up particles into completely free-flowing carbon, particles that are completely free to go about as they want in any direction. And that takes a lot of energy, so that's why your vaporization energy is significantly larger than your fusion energy, which is just taking things in a solid crystal structure and breaking down that crystal structure so that the liquid can flow around each other a little easier. For vaporization, as with fusion, the opposite reaction would be exothermic. So making a liquid into a gas is endothermic. That would require energy. But to go back to a liquid from a gas would need energy to be removed. And this would be the same amount, but negative to go from gas to liquid. And we use this equation, heat is equal to the mass times the change in enthalpy vaporization, to figure out how much heat is required to do those things. So let's take a look now at our whole heating curve. So the whole heating curve, anytime there's a change in temperature, so this part here, 1, this part here, 3, and that's not good. I'm going to use my actual pen. And this part here, 5. Those parts have a change in temperature. Temperature is changing, so we would use to figure out heat the mass times the change in temperature times the specific heat. At that bottom part 1, we would need the specific heat of the solid. At the part 3 here, we would need the specific heat of the liquid, and up here at 5, we would need the specific heat of the gas, but that is the equation we would use. Part 2, so this flat part here at part 2, that is changing from solid to liquid, so that's the delta H fusion. And we would use this equation here if we need to find the heat there. And for part 4, so this part up here, we are turning liquid to gas. So we need to find the heat for that, we need the mass times the delta H vaporization to figure out how much heat is lost there. So how much heat is absorbed when water boils at 100 degrees Celsius? So if we look here at our graph, water boiling is happening at this phase 4. Phase 4 of our graph is where water is boiling. And therefore, we would want to use this equation, Q equals M times delta H vaporization. So Q is going to equal M times the delta H vaporization. And our mass is 8.75 grams. And our delta H vaporization is, there it is, 2260 joules per gram. 2260 joules per gram. And then the grams will cancel, so we get joules for our heat. That is not pretty, but 2260 times 8.75, that's 19775. So Q is equal to 19775 joules. And this is just what we use for that. All right, so what will require more energy? Converting a mole of water to solid to liquid, or a mole of water from liquid to gas? So if we again look at our thing here, a mole of water from solid to liquid is going to happen at this phase here, at phase 2. So that would need a heat of fusion. So a mole of water from solid to liquid, so 1 mole from solid to liquid, is going to need the heat of fusion. So Q is equal to the grams times the heat of fusion. Heat of fusion is 334 joules. So this is 334 joules per gram. For a mole of this, we have to figure out how many grams there are. And for that, grams to moles, we go to the periodic table. H2O, 2 times 1 plus 16. So that's going to be 18 grams in 1 mole. So that's 18 grams times 334. And we find out that's 6012. So that's 6,012 joules for a mole of water to heat up from solid to liquid. To go from liquid to gas, now we're going to need the heat of vaporization. Here, 2260 because we're talking about this part of the graph up here. That's where liquid's here, becomes a gas up there, and that's part 4. And part 4 is going to need the heat of vaporization. So 18 grams again times 2260 joules per gram. It's the same amount. 1 mole of water has 18 grams in it. So 18 times 2260 is 40,680 joules. So as you can see, the amount of energy required to go from liquid to gas is significantly more, almost 10 times as much as the amount of energy to go from solid to liquid. All right, so during practice, you lost 500 grams of water due to sweating. If this water evaporated, how much energy was absorbed from your body? So sweating is looking at what part of our graph here. Sweating liquid to gas is again going to be this part here, number 4. That's where liquid changes to gas. So we're going to go 500 grams. We're using the Q equals mass times delta H vaporization. So that's 500 grams times 2260 for water. Correct. We have that right there, 2260. So 500 times 2260 is 1,130,000 joules for that to occur. So that's how much energy your body loses by sweating 500 grams of water. All right. So the whole picture, the big picture here would be like this. So how much heat is needed to increase the temperature of 250 grams of ice from negative 40? Let's say you're in the Arctic and it's negative 40 and you put it on the boat where it's 0 degrees because the boat's a little warmer. What would be the amount of heat required to do that? So we are changing temperature from 40 to 0 degrees. So if we look on our map here, our phase diagram, changing solid from one temperature to another would happen here at phase 1. So for some reason my pen's not working, but that's all right. I'll just do this. So we're doing it right here. That's where it's happening. And in phase 1, we're going to use heat equals mass times change in temperature times the specific heat. So that's the equation we use for that part of the graph. Our change in temperature from 40 to 0 is 40 degrees. We have 250 grams. We're multiplying it by a 40-degree change in temperature. And our specific heat for solid water is this one here, is 2.06. 2.06. So if you multiply 250 times 40 times 2.06, you get, 250 times 40 times 2.06. There it is. You get 20,600. So the answer there is it takes 20,600 joules to heat that much ice from negative 40 to 0 degrees. All right, so now how much heat it is needed? That same ice is melting at 0 degrees. So if you're melting ice, you're doing a phase change. So you're looking at one of these two flat parts, and solid to liquid is this line here, this line number 2. So we're going to need our heat of fusion. The heat is equal to the mass times the heat of fusion. So in this case, 250 grams times the heat of fusion, which is 334. 334. Oh, it's right there. Why am I doing that? It's right here. Kids, pay attention. I thought I did that. And I did. So 250 times 334 is 83,500. So that's how much heat would be required to heat up that ice, 250 grams of ice to melting. All right. So on this next one, how much heat is required to now bring 250 grams of water from 20 to 100? So let's say you want to boil 250 grams of water. It's at room temperature, and you want to go up to 100. That is using the part of the graph here, 3. We're heating up liquid water. So we are going to use the specific heat part, and that is this here. So the mass is 250 grams. The change in temperature at 20 to 100 is 80 degrees. And your specific heat in this case is you want to use the liquid water one. So it's 4.18. So you multiply those together, 250 times 80 times 4.18, and you get 83,600 as the amount of energy required to do that. Now, how much heat is needed to boil 250 grams of water at 100 degrees? So boiling water, you're looking at phase 4. You're going from liquid to gas. That's what boiling water is. It's 250 grams, and we're going to need the delta H vaporization listed here in the corner, delta H vaporization 2260. So 250 grams times 2260 joules per gram, and that'll give you how many joules it takes to boil water. So the point of these questions is just basically which area of the graph are you using, and then you use that equation, and that's going to be 565,000 joules. 565,000 joules for that to happen. All right, so that is basically what your test is going to be. Enjoy. I hope this helped, and I'll talk to you about it more this week.